Hello, welcome to another module in this massive open online course. So, we are looking at example problems in the Fourier analysis of discrete time signals, in particular the DTFT, that is a Fourier analysis of discrete time aperiodic signals. So, let us continue our discussion. So, we want to look at example problems on the DTFT, correct. So, we are looking at example problems on the DTFT, discrete time Fourier transform. Let us look at example number 6, it's fairly simple, that is the inverse DTFT, the IDTFT. So, we want to find the IDTFT of this function, this signal, that is 2 pi delta omega minus omega naught, and what is this? And the IDFT can be found as follows. This is 1 over 2 pi integral over any interval minus pi to pi delta omega minus omega naught e raised to j omega n d omega. In fact, this is 2 pi delta omega minus omega naught. So, let me just correct that. This is 2 pi delta omega minus omega naught, and this will be, now the 2 pi's cancel, this will be integral minus pi to pi delta omega minus omega naught e raised to j omega n d omega, which is basically e raised to j omega n. You substitute here omega equals omega naught, and this will be e raised to j omega naught n. So, that is the inverse. So, we have e raised to j omega naught n, basically that has your discrete time Fourier transform 2 pi delta omega minus omega naught, or basically that 2 pi delta minus omega naught has the inverse discrete Fourier transform, that is e raised to j omega naught n. So, this illustrates how to compute the inverse discrete Fourier transform. All right. Now, let us apply this result to compute the discrete Fourier transform DTFT, discrete time Fourier transform, I am sorry, inverse DTFT of cosine omega naught n, and the DTFT of cosine omega naught n. What is the DTFT of cosine omega naught n? And remember, cosine omega naught n can be written as cosine omega naught n equals half e raised to j omega naught n plus half e raised to minus j omega naught n. E raised to j omega naught n has DTFT 2 pi omega minus omega naught, we have, as we have seen before in the previous example. So, half e raised to j omega naught n has DTFT pi delta omega minus omega naught. Similarly, half e raised to minus j omega naught n will have the DTFT pi delta omega plus omega naught. So, this will have half times 2 pi delta omega minus omega naught plus half into 2 pi delta minus omega naught, that is delta plus omega naught. So, this will be equal to basically pi delta omega minus omega naught plus pi delta omega plus omega naught. So, cosine omega naught n has the DTFT pi delta omega minus omega naught plus pi delta of omega plus omega naught. Okay. Let us continue to another example. We want to find the inverse DTFT let us find the inverse DTFT of the given signal of, let us call this y of omega. Omega equals or let us just call this inverse DTFT of the given DTFT, that is 1 minus a e power minus j omega whole square, and also given the condition that magnitude A is strictly less than 1. So, we are required to find the inverse DTFT of this signal. Now, let us start by considering the signal xn is to equals a raised to the power of n un, alright, where a is magnitude A is less than 1, alright, and we will manipulate the DTFT of this signal to derive the inverse DTFT of the given DTFT. Okay. So, we start by considering, because this is related to the DTFT of an, the exponential signal, that is a raised to the, or the decaying signal a raised to the n un. If you look at the DTFT of this, you have x of omega equals 1 minus a e raised to minus j omega. Okay. Now, if you differentiate this, with respect to omega, you will have minus or you will get, first you will get minus 1 over 1 minus a e power minus j omega whole square, correct, multiplied by, now derivative of minus a e raised to minus j omega, that is minus a e raised to minus j omega, derivative is minus j omega times minus j. Okay, and this will basically be, now if you simplify this, this is minus j a e raised to minus j omega divided by 1 minus a e raised to the minus j omega whole square, that is your dx omega by d omega, that is the derivative of x of omega, which implies that j dx omega by d omega will be equal to, multiplying both sides by j, you will have minus j into j is 1. So, this will simply be on the right hand side a e raised to minus j omega divided by 1 minus a e raised to minus j omega whole square. Okay. So, that is basically your corresponds to your j times the derivative of x omega with respect to omega. But realize that j dx omega by d omega, that corresponds to, if x omega is the DTFT of x of n, j dx omega over d omega, that corresponds to the DTFT of n times xn. So, which means this corresponds to, this is the DTFT of the signal n. So, this j dx omega over d omega, this is the DTFT of n xn. So, this is basically the DTFT, because we know x of omega corresponds to a n u n. So, this is n times xn, that is n times a n u n. Okay. So, that is your a e power minus j omega by 1 minus a e raised to minus j omega whole square. Okay. Now, let us simplify this quantity, a e raised to minus j omega divided by 1 minus a e raised to minus j omega whole square Okay. So, this corresponds to, or let me just write it this way, n a raised to n u n, this has DTFT, that is your a e raised to minus j omega divided by 1 minus a e raised to minus j omega whole square, which implies if you take the negative of this minus n a raised to n u n, that has the DTFT, which is given by minus a raised to minus j omega by 1 minus a e raised to minus j omega whole square. Now, you can add and subtract 1. So, that will be basically equal to 1 minus a raised to minus j omega minus 1 over 1 minus a e raised to minus j omega whole square. Now, this you can simplify as 1 minus a e raised to minus j omega by 1 minus a e raised to minus j omega whole square. So, that is 1 over 1 minus a e raised to minus j omega minus 1 over 1 minus a e raised to minus j omega whole square. Okay. And now, you know that this quantity 1 over 1 minus a e raised to minus j omega, that has the inverse discrete Fourier transform, that is x of n. Remember, this is simply x of omega. So, that is the inverse discrete Fourier transform, that is x of n, which is a n u n. The rest, the remaining term is corresponds to basically the quantity for which we want to find the inverse discrete Fourier transform. So, if you take the inverse discrete Fourier transform of this, you will get a x n, that is a to the power of n u n, and taking the inverse discrete Fourier transform of this, we get, let us call this x tilde n, where x tilde n is the inverse discrete Fourier transform of the quantity 1 over 1 minus a e raised to minus j omega whole square, which is the given DTFT. Okay. So, this implies basically what you have is n a raised to n u n is a to the power of n, or in fact minus n a raised to n u n is a raised to the u n, a raised to the n u n minus x tilde n, which implies that x tilde n is n a raised to n u n plus a raised to n u n, which is basically equal to n plus 1 into a raised to the n u n. Therefore, the inverse discrete Fourier transform of the given quantity is n plus 1 a raised to the power of n u n. Okay, or you can say n plus 1 a raised to the power of n u n has the discrete time Fourier transform 1 over 1 minus a e raised to minus j omega whole square, where magnitude of a is less than 1. Okay. So, this is the basically this is the inverse DTFT of given quantity. IDTFT this is the inverse DTFT of the given quantity. Okay. Now, another way to do it will be as follows. Now, another way to do it will be as follows. So, you can see basically that look at this, I have the given DTFT is 1 over 1 minus a e power minus j omega whole square, that is equal to 1 over 1 minus a e power minus j omega times 1 over 1 minus a e power minus j omega. Now, if you look at it, this is basically the multiplication in the Fourier domain, the DTFT domain, which means it must be the convolution of the corresponding inverse DTFTs. This is corresponding time domain signals. The corresponding time domain signal for 1 over 1 minus a e raised to minus j omega is a raised to n un. So, this is basically, if you take the inverse DTFT, this corresponds to basically the inverse DTFT corresponds to, this is the multiplication in the Fourier domain. So, in the time domain, in fact discrete time domain, this is the convolution of the corresponding inverse DTFTs, which is a raised to n un. And that convolution is basically, I can write it as summation k equals minus infinity to infinity a of k u k into a of n minus k u n minus k, which is basically equal to a of k into a of n minus k is a of n, which is does not depend on k, hence comes out of the summation. Now, if you look at summation k equal to minus infinity to infinity u of k into u of n minus k, this is non-zero only for this summation, you can see is non-zero only for k greater than or equal to 0 and k less than or equal to n, alright. So, this summation for n greater than or equal to 0 will be, I can write it as, for n less than 0 it is 0, for n greater than or equal to 0 this is simply a raised to n k equal to 0 to n times 1 for n greater than or equal to 0. So, this is basically n plus 1 a raised to the n for n greater than or equal to 0, and you can write this as n plus 1 into a raised to the n un. Okay, so, this is another way, again this is the IDTFT of the given signal, which seems to be a slightly simpler way to derive the same result. Alright, both approaches yield the same answer. These are two different approaches, one is by differentiation and the other is by simply realizing that it is a convolution of two known signals in the time domain. Okay. Alright. So, let us do another example problem. So, this was problem number, I believe problem number 8. So, we will have problem number 9. So, problem number 9 is as follows. This is again another standard problem to find the inverse, to find the DTFT of u of n, the unit step function. What is the DTFT? Remember, u of n equals 1 for n greater than or equal to 0, 0 for n less than 0. So, this is basically your x of n. I can write u of n as x of n plus y of n, where x of n equals half for all n and y of n equals half for n greater than or equal to 0 and minus half for n less than 0. Okay. So, I can write it as x of n plus y of n, where x of n is half for all time samples n and y of n is half for n greater than or equal to 0 and minus half for n less than 0. Okay. Now, if you look at the DTFT of x of n equals half for all n implies this is basically x of omega equals half. So, if you look at 1, remember 1 has the DTFT 2 pi delta omega. So, this implies half has the DTFT pi delta omega. So, x of n equals half implies x of omega equals pi delta omega. So, that is the first point. Now, if you look at yn, which is half n greater than or equal to 0 and minus half n less than 0, if you look at yn minus 1, that is equal to delta n, okay, yn minus 1 equals delta n. This implies y omega into, that is by the time difference property, 1 minus e raised to minus j omega equals, taking the DTFT of delta n, that is 1, which implies y omega equals 1 over 1 minus e raised to minus j omega. And finally, we have the given sequence is xn minus plus yn, un we have written as xn plus yn. By linearity, we have u of omega equals x omega plus y omega, implies u of omega equals, this equals x of omega, which is basically pi delta omega plus y of omega, that is 1 over 1 minus e raised to minus, that is the DTFT of the standard unit step function, unit step signal. So, this is basically your DTFT of unit step. This is the DTFT of the unit step signal. Okay. All right. Now, let us look at the accumulation property, that is the next property, which is the accumulation property. So, continue in the same example. What is the accumulation property? Consider y of n equals summation k equals 0 to n x of k. So, let us say xn has the DTFT x of omega. What is the DTFT of y of n? This is the accumulation property. Remember, this is termed as the accumulation property of the or this system is termed as the accumulator, accumulation property all right. This is the accumulation property, is similar to integration in the continuous time, correct. This is similar to integrate, that is you are integrating signal input signal x tau from minus infinity to t or 0 to t. This is known as the it is known as the integrator, right. So, similarly this is the accumulator. Okay. So, this is similar to the integrator for continuous time signals, and you can see now realize very simply that yn is nothing but basically summation k equals 0 to n xk, which you can see is nothing but the convolution of xn with un, because convolution of xn with un is similar simply xk equals minus infinity to infinity xk un minus this simply convolution from, sorry, this has to be, I think this is convolution from minus infinity to n. Okay. So, this is basically, you can see this is simply k equal to minus infinity to n, all right, and un minus k, this is non-zero only for k less than or equal to n. So, this is basically summation k equals minus infinity to n x of summation k equal to minus infinity to n x of k, correct. So, all right. So, basically what you have is that implies Now, convolution in time in frequency domain it becomes multiplication. So, implies y of omega, which is the DTFT of the accumulator, is basically x of omega times u of omega. This is simply x of omega, and we have derived the DTFT of the unit step function u of omega, that is given as pi delta omega plus 1 over 1 minus e raised to minus j omega, okay, which is pi times x of omega times d of omega plus x of omega over 1 minus e raised to minus j omega. And now you can see that x of omega into d of omega, that is nothing but x of 0 from the properties of the unit impulse function, right, the the discrete time impulse function. This is simply x of 0 into delta of omega. So, this is also pi of x of 0 delta omega plus x of omega over 1 minus e raised to minus j omega, alright. So, basically that is basically your accumulator. So, that basically gives the DTFT of the accumulator. So, that basically gives the DTFT of the accumulator, alright. So, with that let us stop this module here, and we will continue looking at similar other problems in the subsequent modules. Thank you very much.